To pre-train a massive language model today, you need tens of thousands of GPUs running continuously for months. Look at the top rows of this chatbot arena leaderboard. Deepseek R1 matches top models in hard prompts and coding, placing it among the most advanced AI systems in existence. Getting a model to that level of performance usually requires a stage called supervised fine-tuning. Engineers feed the network thousands of step-by-step examples of human logic, teaching the algorithm to imitate how humans arrive at a correct answer. But human data is limited. When we solve problems, we rarely document our internal false starts or our silent verifications. Because humans provide the training data, the model only learns a polished, incomplete approximation of thought. This creates a mathematical ceiling. If a model is trained strictly to replicate human demonstrations, it cannot explore reasoning pathways that are mathematically superior to human intuition. Forcing an AI to perfectly replicate human thought processes caps its potential at the level of its teachers. Deepseek R1 tests a different hypothesis, that advanced reasoning can emerge organically through pure, unconstrained reinforcement learning. The researchers started with Deepseek V3 Base. They deliberately skipped the traditional supervised fine-tuning phase entirely, providing the model with no human examples of how to reason. By bypassing human-defined patterns, the researchers allowed the model to explore a drastically wider latent search space. Instead of predicting the next most likely token based on human text, the model uses dynamic trial and error. It attempts a solution, receives a reward for correctness, and optimizes its internal strategy. To engineer an intelligence that surpasses human logic, we must stop giving it a script and start giving it an incentive. GRPO algorithms sample 16 parallel output branches per question. These are scored purely on final correctness using strict rule-based rewards, like a compiler. A format reward then forces the model to enclose its search inside think tags, revealing its reasoning. Crucially, the team avoided using neural reward models to grade the reasoning process itself. They chose not to have one AI model judge the quality of another's thoughts. This prevents reward hacking. As this chart shows, when a neural verifier is used, a model eventually learns to manipulate the grader to get a high score, even as its actual performance on the task drops. By sticking to simple, unbreakable rule-based rewards, the system generates more robust reasoning than complex, hackable neural evaluators. We can see the impact of this approach at the 8.2K training step. This is a critical inflection point where the model's accuracy on math competitions suddenly jumps from 15% to nearly 78%. At this point, the model developed dynamic token allocation. It autonomously learned to generate thousands of extra thinking tokens to solve harder problems, spending more time on verification and backtracking. During one intermediate version of the training, the model began to self-reflect in a human-like tone. It typed, wait, let's reevaluate this step by step to identify if the correct sum can be. The sudden use of words like wait, mistake, and retry was not programmed into the model. Instead, it was discovered organically by the algorithm as the most effective survival strategy for securing a reward. This backtracking behavior is the mathematical equivalent of self-doubt. The model is checking its own logic against the rules it was given. The system wasn't taught how to think. It mathematically deduced that pausing to reflect is the most efficient path to a correct solution. However, this pure reinforcement learning model, known as R10, had severe usability issues. It often mixed multiple languages in a single response and lacked the readability required for human interaction. To bridge this gap, the team developed a multi-stage pipeline, refining the R10 engine into a deployable tool. They began with a cold start phase, injecting thousands of high-quality reasoning trajectories to anchor the model's tone into a human-aligned format. Next, they used rejection sampling. A secondary model filtered the data to remove chaotic language mixing and enforced structural consistency across the training set. A final stage of reinforcement learning used human alignment data to ensure the model's outputs remained helpful and harmless when used for open domain questions. Unconstrained computational search is powerful, but it requires a structured, human-aligned filter to be useful in the real world. The full Deepseek R1 is a 671 billion parameter network. It uses a mixture of experts architecture, activating a fraction of its parameters for each token. Despite its efficiency, running a model of this scale during inference still requires significant energy and high-performance hardware. To democratize access, the researchers used model distillation. They took 800,000 reasoning trajectories generated by R1 and used them to fine-tune smaller, efficient architectures like Llama and Quen. These distilled models dramatically outperform their original versions because they inherit the specific deductive pathways R1 discovered through its massive reinforcement learning process. High-performance machine logic is no longer locked behind massive corporate server farms. It can now be run locally on consumer-grade hardware. This accessibility creates a major security risk. A model with high verifiability reasoning provides significantly higher operational feasibility for dangerous or illegal requests. Because Deepseek R1 is open-weight, its intrinsic safety layers can be bypassed, making it more vulnerable to jailbreak attempts than closed models. Safe professional deployment requires a system-level risk control framework. When a user submits a query, an external system reviews the potential risk and uses a secondary model to determine if the response should be retracted. Because reasoning models can solve complex problems, these systems often show higher rejection rates, as they must be more aggressive in preventing the model from explaining harmful procedures. We are witnessing a shift from models that simply parrot human knowledge to models that optimize for a result. By pairing a verifiable objective with unconstrained compute, we are allowing AI to discover more efficient paths to a correct solution than human intuition could ever provide. Today's video was brought to you by Synestex Systems, LLC, founded by Shane Persinger.